everybody. We are going to focus back on chapter 12, which there's a section in chapter 12 that talks about inter and intramolecular forces. So that's what this video will be discussing today. On your slides, I just went over the inter and intramolecular forces. So I will post new slides that have to deal with the liquids and the solids probably tomorrow. Just a heads up, if you have a snow day tomorrow, then there will be another video for your blog for homework tomorrow as well. So you will have this one, and then you will have another video if we have a snow day. If there's not a snow day, then we'll cover that content in class. So you have this video tonight. If you have a snow day tomorrow, then you will have a video also posted tomorrow morning for you to watch as well. On Thursday, you're going to have a quiz that's going to be over the majority of this section that we've been talking about, starting with chapter 12, which has to do with gases, and then going into all of the gas laws. We'll also cover the inter and intermolecular forces on the quiz, and then whatever's on your video tomorrow, which should be over liquids and solids. So it should take us mostly through all of chapters 12 and 13. So if you will look at the first slide for me that's posted, I wrote on here some objectives for you. So it just says that our objective in this is to describe intramolecular forces, and then we want to compare and contrast intermolecular forces. Now, we have talked about both, but we're just going to go back through and really, I think, give a better job of explaining the differences or comparing intermolecular forces, okay? Another thing for review, polar covalent, we kind of reviewed that a little bit today in a few classes. I don't think that 6th Bell we got to that today. But this new vocabulary that's also on the slide is really not new. We've heard about these things. We've seen dispersion forces, we've seen dipole-dipole, and we've seen hydrogen bonding. So all of those things should be kind of a review. They shouldn't be so much new. If you'll go to the next slide, we see I have a question of the day. And that is, if all particles of matter at room temperature have the same kinetic energy, why are some materials gases and then other materials liquids or solids? So if all particles of matter at room temperature have the same kinetic energy, because they're at the same temperature, right? So their average kinetic energy should be the same. Why are some of them gases, but then some of them liquids or some of them solids? The answer to this is because each of these pieces of matter have attractive forces between or within the particles, and that's the big thing. So because of attractive forces within or between particles, this is what causes some things to be gases, some things to be liquids, and some things to be solids. So if you go to the next slide, I have a little thing set up for you to write some notes down about the differences between intramolecular forces versus intermolecular forces. So for intramolecular forces, the word intra, or the prefix intra, means within. So that means that I actually have some type of attractions happening within the molecule. So if I think about this, if I had, let's just say, for example, CO2. Let's say that I have carbon dioxide. The intramolecular attractions would be based on the bonding type. So since I have carbon dioxide, that's a molecular compound, and molecular compounds contain covalent bonds. So the intramolecular force that's found in carbon dioxide would be covalent bonding. So intramolecular forces, we know that we've studied so far at least 3 types. There's ionic bonding, there's covalent bonding, and then we've also talked about metallic bonding. So intramolecular forces is meaning the forces that are acting within the molecule or within the formula unit or within that particle. And we have 3 types: ionic bonding, covalent bonding, and metallic bonding. And I think on the next slide, we'll get into some more specifics about those 3. In intermolecular, so we've had intermolecular forces, the prefix inter means between or among. So intermolecular forces would be the dispersion forces, the hydrogen bonding, and dipole-dipole forces. And that happens not in the molecule, but outside of the molecule. So it happens when molecules interact with other molecules, okay? And again, so we have three types of intramolecular, that's ionic, covalent, and metallic. And then we have three types of intermolecular, which would be hydrogen bonding, dispersion forces, and dipole-dipole. Now, one other really big thing that I would like you to add to this slide of intramolecular versus intermolecular is that all intermolecular forces are weaker than intramolecular. So intermolecular, so the forces that happen between the particles are not as strong as the forces that are happening within the particle. And just think about that. If I need a particle to stay together, what makes it really important is the intramolecular, what's keeping it together. If it's not together, I can't have intermolecular forces, because then those particles, how are they going to interact? How can I have hydrogen bonding? How can I have dispersion forces? Or how could I have dipole-dipole interactions? So the intermolecular forces are not as strong as intramolecular. So covalent bonding, metallic bonding, ionic bonding trumps the intermolecular forces, okay? So if we will now go to, so we did the intra versus intermolecular. If you'll go to the fourth slide for me. This is just talking about intramolecular. So we have, again, like we said, three types. There's ionic, there's covalent, and there's metallic. And we know that ionic bonding happens between a cation and an anion, or we can think about that as a metal and a non-metal. We could think about that as a metal and a polyatomic ion. But typically it happens between a cation and an anion. So I have a positive charge attracted to a negative charge, and those opposite charges are keeping that attraction. That's what's keeping them bonded together. In the covalent bond, as we can see here on the chart, that happens, that attraction is due because I'm sharing electrons. So we know that for covalent bonds, it typically happens between two nonmetals, and they're going to end up sharing some electrons in this bond. And we know that that's not as strong of a bond as ionic bonds are, but covalent bonds are still a pretty strong bond, since it's an intramolecular force. It's the force that's happening within that particle. The third type is metallic, which we know that metallic bonds happen in metals. So if I have some metals, and that happens because I have all of these cations, and I have those sea of electrons that are just kind of like moving around all of those cations. So they're making them able to like flow and move around, which is why they're so ductile or malleable. So those are the intramolecular forces. And now we want to go to the next slide, where we're going to go in more in depth about the intermolecular forces. So again, we've talked about these before, but I think that we covered maybe a surface level, and we want to go a little bit deeper. So first type of intermolecular force, which again just means the force between or among particles. First one we're going to talk about is dispersion forces, and we know that it says here dispersion forces are weak forces that result from temporary shifts of electrons in electron clouds. So remember that when we talked about this, we said that dispersion forces happen because those electron clouds of different particles come in contact with each other. And when you have two like things that are coming in contact, what are they going to do? If I have two north ends of a magnet and I bring them close together, they're going to repel. So that's exactly what these are going to do. They're going to repel. Now, since those electrons are constantly moving in that electron cloud, they're in constant motion, when these two molecules or these two particles come in close contact, then those electron clouds, like we said, they're going to repel one another for a moment. Now, we talked about that the last time, so some of the more deeper stuff that I want to get into is that for this moment when those electron clouds repel, what's going to end up happening is you're going to get a bigger electron density in one region of the molecule than the other region. So it's going to act like it's making a dipole. It's a temporary dipole. But because those electrons are repelling one another, all of the electrons in this molecule are going to push this way. All of the electrons in this molecule are going to push this way. So I have more electrons on one side of the molecule. When that happens, we know then we can get some type of dipole, which means partial charges are created. So I have some type of partial charge. Because of these temporary dipoles, these dipoles can temporarily interact with one another, kind of keeping some of those particles closer together. So because these electron clouds can repel, they can also create a temporary dipole. So temporary meaning that it's not going to stay as that dipole. They're going to repel. It's going to happen for a moment where I get a temporary dipole. I may have some attraction. After that, it's done. It'll go back to being normal until those electron clouds repel again, and then the same thing's going to happen. So dispersion forces exist between all particles because at some point, since they're always moving, I'm always going to have some type of electron cloud next to another electron cloud. When that happens, they repel, I get a temporary dipole, temporary partial charges, and then that means that because of these temporary dipoles, they're going to be a little attracted to one another. Now, again, they exist between all particles, and dispersion forces are pretty weak for small particles. And that's just because I can't create a huge dipole with just really small particles. But if I increase the number of electrons, let's say I have a really big particle, a really big molecule, and I increase the number of electrons, then the dispersion force would also increase. So the more electrons I have, the more of a dispersion force I'm going to feel between those particles in that sample. And I would like us now to move on to the next slide. So that was dispersion forces. The second force, the second intermolecular force that we're going to talk about are dipole-dipole forces. And it's very similar to kind of like what we were just talking about with dispersion forces. It says dipole-dipoles are attractions between oppositely charged regions of polar molecules. Big key here is it has to be a polar molecule because polar molecules have dipoles. So we know that polar molecules have a partial positive charge and a partial negative charge. So polar molecules contain permanent dipoles. They will always have partial positive, partial negative end for the molecule. So because we have a partial positive and a partial negative end, if I orient that and I look at my picture here, I see that I have one molecule, I have one end of a molecule that has a green sphere to it, and then the other end that has like blue color to it. So the green sphere is at partial negative, and that blue sphere is a partial positive. So the partial positive would prefer to be next to the partial negative. Why? Because opposites attract. So they want to orient themselves so then that way they're making sure that they are attracted to that opposite charge. And that's exactly what just dipole-dipole forces are. We have some type of attraction, and those neighboring polar molecules will rearrange themselves constantly so then that way they can be aligned with an oppositely charged region. So partial positive wants to be next to the partial negative of another molecule. Partial negative of one molecule wants to be next to a partial positive of another molecule. So they're going to, again, continue to orient themselves until they have all of that opposite attract kind of rule going on. So comparing the last two forces, so we've talked about dispersion forces, and then we also have dipole-dipole forces. Now, which force would be greater, dispersion forces or dipole-dipole forces? It depends. It depends on what you have. So small polar molecules that have large dipoles will that force, the dipole-dipole force, will be stronger than a dispersion force. However, many polar molecules that are really big end up, the dispersion forces would be much larger, or that force tends to be much greater than the force of dipole-dipole. So when I ask you which force is greater, dispersion or dipole-dipole, I would want you to say that dispersion forces, if polar molecules are large, would be greater. But if polar molecules are small, then I would say that dipole-dipole forces would be stronger, okay? So there's kind of more of a catch to this one. Last one, if you go to the next slide, your last intermolecular force is hydrogen bonding. And hydrogen bonding is just a type of dipole-dipole force or dipole-dipole interaction. And specifically, it's that attraction between hydrogen and then one of three elements. That's fluorine, nitrogen, or oxygen. So hydrogen bonding is a dipole-dipole interaction. It's a type of that. And it happens when hydrogen is attracted to nitrogen, oxygen, or fluorine. And those are typically the most electronegative elements. So that's why it wants to be attracted to that. And let's kind of talk about why. For these hydrogen bonds, we want there to be a large dipole, a large partial negative charge, and a large partial positive charge. And that's what's really creating this hydrogen bond. That is why hydrogen bonds are considered to be the strongest of all intermolecular forces, because their dipoles are so large, because hydrogen, fairly weak electronegativity, and then compared to oxygen, fluorine, and nitrogen, which has much of a larger electronegativity, when those two things are attracted to one another, then I have a huge difference between that in that dipole. So it's just a nice big difference there, a nice big dipole difference. So again, hydrogen bonds, hydrogen is attracted to nitrogen, oxygen, or fluorine, and it is the strongest intermolecular force, okay? On the next slide, and this would be pretty much the last slide we're going to talk about, I put this chart on here because I think it's kind of cool. It gives us an example of hydrogen bonding kind of in action. So hydrogen bonds explain why water is a liquid at room temperature, while a lot of compounds that have similar masses to water are mostly gases at room temperature. In this chart, we're comparing water, methane, and ammonia. So if I gave you the molar masses, and then you were also given the boiling points of those as well. So methane is nonpolar, and I know that because carbon and hydrogen, their electronegativity differences are so similar that it gives me that electronegativity difference between 0 and 0.4, which makes it nonpolar. And I know that nonpolar molecules don't have dipoles. So if they don't have dipoles, then really the only thing that's kind of keeping those molecules together, keeping methane molecules together, would be dispersion forces. So that's kind of like taken out of the picture because there's not really any hydrogen bonding there. In terms of ammonia and water could both exhibit some type of hydrogen bonding, because ammonia contains nitrogen and hydrogen, and then water contains oxygen and hydrogen. So hydrogen could be attracted to nitrogen in ammonia, and oxygen could be attracted to hydrogen in water. So both of those can exhibit hydrogen bonds. The difference between them is that water is bonded with oxygen, and oxygen is just more electronegative than nitrogen is. So because oxygen is more electronegative, the OH bonds in water have a stronger polar bond, and that makes it stronger. So because it's stronger, it acts more as a liquid. There's more attraction holding them together. Versus in ammonia, it's not as strong of an attraction, so I have more space in between those particles, thus giving me a gas. Okay? Now, if you go to the next slide, I just have a little question where a hydrogen bond is a type of, and you would look at, I could have, is it a type of dispersion force? Is it a type of ionic bond? Is it a type of covalent bond? Or is it a type of dipole-dipole? Be a type of dipole-dipole force. If you go to the next one, which of the following molecules can form hydrogen bonds? Would it be carbon dioxide, Would it be C2H6? Be NH3, ammonia? Or would it be hydrogen H2? So in that case, I would look if I had a hydrogen attached to nitrogen, oxygen, or fluorine. And the only case that I see that for is C. So the correct answer there is C. Okay, so again, if you have questions, post them on the blog for me. And if I don't answer them immediately tonight, I will answer them in the morning if we have that snow day. Also, you should make sure that you're checking to see if we have a snow day tomorrow, because if so, you will have another video, and I'm going to go over the liquids and the solids, and that'll finish up our chapter. On Thursday, regardless if you have a snow day or not, you will have a quiz on Thursday, and on Friday, we're going to do a lab, okay? So I will maybe see you guys tomorrow, but hopefully we have a snow day, and flush ice cubes down your toilet, wear your pajamas inside out and backwards, and Mr. Mater says to spit out your car window. Never heard that one before, but hey, if Mater says it, you should do it, okay? Bye.